An inquiry could be established to examine Victoria's decision to demolish public housing towers and the impact it would have on thousands of residents.
We will demolish those towers.
How are we going to get it? Fight for it!
No public housing will be rebuilt on the site.
More than 40 public housing towers across Melbourne on the chopping block.
There is no reason to be selling our very valuable public land.
With a report arguing the government could save time and millions of dollars by renovating instead of raising.
They are old, they are out of date, they are no longer fit for purpose.
Today we are looking at the 1960s public housing towers. Now there's been quite a lot of discussion in the media with respect to these towers. The Victorian government is looking to knock down around 44 of these towers as part of their 30-year plan to progressively redevelop the sites upon which these towers are built upon. Shearforce Engineering have been part of a team of architects and engineers who have been studying these towers to determine the feasibility to rejuvenate and reuse them for decades to come. Towers of various forms are dotted around the suburbs of Melbourne. Some of the most well-known include Fitzroy, Flemington and South Yarra. From a logistics point of view, these towers were constructed back when government actually built things. The Victorian Housing Commission oversaw the entire process, from planning to design to the actual construction of the towers. The precast concrete panels used in the construction of the towers were produced at the Housing Commission's very own factory in Holmes Glen. From a structural engineering perspective, these towers are fascinating to study. The 1960s saw the fledgling beginnings of the sophisticated precast concrete industry we know of today. Out of the factory at Holmes Glen, precast concrete was manufactured for single-storey dwellings, power poles, fence posts, as well as the panels which were used in the Housing Commission towers. For its time, the operations within the factory were at the cutting edge of precast manufacturing. It was an end-to-end operation where the concrete was mixed and batched on site. The Housing Commission partnered with the CSIRO at the time to formulate what was an innovative lightweight concrete mix that was 20% lighter than conventional concrete. After the concrete was mixed and batched, it was then delivered to the heart of the factory at the assembly line. The assembly line comprised an array of constantly moving forming tables, which the factory workers would install the formwork for the ends and the openings within the panels and fix the reinforcement. The panels manufactured in the Holmes Glen plant weren't just used in the Housing Commission high-rise towers. They were also used in single detached dwellings throughout Victoria. So for all their innovation, how have the Housing Commission towers fared through the last 6 decades of continuous service? Are they indeed still fit for purpose? And can they be retrofitted to meet current design standards? Well, design standards have changed considerably since the 1960s. The most notable advancement has been that of seismic design. The first formal seismic design code was published in Australia in 1979. Therefore, most buildings built prior to this time are likely not up to scratch when it comes to seismic activity. The seismic design code then received a significant revision following what has been called Australia's first killer earthquake, which occurred in Newcastle in 1989. So let's take a closer look at these towers, and this comes with a warning. We will be delving into some structural engineering principles and details when looking at how these buildings fare against current design standards. Here is a plan view of the specific tower we studied as part of our assessment. We've affectionately called this tower the S-type tower, given its geometry when viewed from above. It's about 70 metres long and 28 metres wide. Apartments are stacked horizontally, extending to the end of each wing of the tower. A communal corridor allows access to each dwelling, and fire circulation stairs are provided near the extremities of each wing. Centrally, there is a lift shaft housing 2 lifts, a communal area, laundry, and plant areas. The Housing Commission towers use precast concrete for the majority of the construction. Let's zoom in on this right-hand side wing and take a closer look. The party walls between each dwelling provide primary load-bearing support to the floors, and also a significant degree of lateral support for wind and seismic loading. The floor structure is a checkerboard arrangement of precast panels which are orientated in this fashion. With seismic design, the devil is always in the detail, so let's take a closer look at the junction between the primary precast load-bearing walls and precast floor segments. In terms of construction sequence, the first precast panel was landed. Then temporary propping and wedges are put into place. The precast floor segments were then lowered into position. The ends of the precast panels were provided with protruding reinforcing bars where the ends of the floor panels meet the primary load-bearing walls. A first pour of grout was then applied between the ends of the floor panels and directly underneath the bearing surface between the soffit and load-bearing wall beneath. Loose steel flat plates were then welded to the protruding reinforcing bars in order to allow the floor system to act continuously over the load-bearing walls. This essentially allowed the precast floor system to behave more like an in situ slab, which enhanced its performance. A handful of small saddle props were then placed into position, ready to provide temporary support to the primary wall above. The primary wall above was then lowered into position onto the saddles. A secondary grout pour was then introduced, which provided full bearing contact to the primary wall above and encased the welded plates and protruding reinforcing bars which projected out the ends of each floor panel. The temporary support saddles were then removed, and the process was repeated some 20 additional times until the roof level was reached. If you are wondering where the positive connection is between the primary wall above and primary wall below, the answer is that for the majority of the load-bearing wall panels across the breadth and height of the tower, they don't exist. That's right, the tower would appear to resemble that of a house of cards. Preventing the tower from toppling over under a strong wind gust is a combination of friction and the weight of the tower itself pinning it down. We have assessed the tower based on current code requirements for wind, and we've found that theoretically this actually works. However, just because something works doesn't mean you should do it. Or to put it another way,
your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should.
So the towers as they currently stand are theoretically stable under design wind conditions. However, when you ramp up the horizontal load into the seismic realm, things become a little more interesting. The overturning moment due to a seismic event is simply too much for the towers to handle under their current detailing. What makes things even more challenging is that the reinforcement detailing within the precast walls themselves mean that the building behaves in a non-ductile manner due to earthquake shaking, which increases the seismic demands on the building. So does this mean that the towers are doomed? Well, our view is not necessarily. In fact, we have successfully resurrected ruins of structures in order to meet current code compliance. There are a number of different options to explore when strengthening existing buildings for seismic requirements, and these are explored for the S-type tower. One possible solution to help assist with the ductility issues and lack of positive connection between the load-bearing walls is the introduction of retrofitted steel plates bolted to each side of the precast walls. An alternative to this is to adopt carbon fibre strengthening to achieve a similar outcome. These buildings have a lot of walls, so the labour and materials involved with either solution will be quite considerable. However, is the cost associated with these works more significant than knocking down the buildings and starting again? Well, the detailed study which we have been a part of indicates that significant cost saving can be achieved through strengthening and upgrading the buildings. As part of this study, other non-structural upgrades have been included as well, such as increased facade openings for more natural light, enlargement of living areas, new kitchens and bathrooms, upgraded heating and cooling systems, and double glazed windows. The study has been performed specifically on the housing estate in Flemington and has found that retrofitting and upgrading the existing buildings will result in a cost of $400,000 per dwelling, whereas the proposal to demolish and rebuild would cost $680,000 per dwelling. The study has also found that retrofitting and upgrading the existing buildings would result in a 55% reduction of global warming potential compared with a knockdown and rebuild. On top of this, demolishing the buildings will result in significant social impacts to the communities of people who have lived in these towers, in some cases over multiple generations. This full report has now been released for public viewing. Much of the criticism squared at the Victorian government's decision to demolish these buildings has been due to a lack of transparency when arriving at this decision. The release report aims to provide that transparency, which appears to be lacking. If you'd like a copy of the report, feel free to reach out. In the meantime, the hearing for this matter will recommence in the Supreme Court in the coming weeks. We will eagerly watch on to see the outcome and the decision. Thanks a lot for watching.